The photoelectric effect gets really interesting when we start to investigate what happens during the experiment. So you're given a scenario here, and you're told that a current is flowing for some particular wavelength and intensity of light, and then you decrease the photon wavelength. And you have to predict what will happen to these two variables, so the photocurrent and the maximum kinetic energy of the electrons. So, to figure this out, we need to know something about the physics of the situation. So first, let me just tell you what actually happens, and then we'll explain why. It turns out, in this circumstance, the photocurrent, which is the rate of electrons being ejected, will not change. So that's unchanged. However, the maximum kinetic energy of the electrons will increase. So why is this? Well, let's consider what we've actually done to the light by decreasing the wavelength. We know that the energy of a photon is linked to its wavelength through the equation E equals hc over lambda. So by decreasing wavelength, we have increased the energy per photon. Now, to gauge the effect this actually has on the electron ejection process, let's consider what is really happening at an atomic level in this experiment. So we have atoms. Take this to be the nuclei of the metal. So that's a nucleus. And around that nucleus, we have electrons. Now, the reality of this is obviously a lot more complicated. The electrons don't exist as little spheres orbiting around the nucleus. But for the sake of this explanation, that doesn't really matter. What we're really interested in is the energy level of the electron when it's around the nucleus. So basically this electron is going to be in a potential well. I'll put a little electron symbol there. It's in a potential well. So this is analogous to us in Earth's gravitational well. We're in some negative energy, negative potential energy hole, essentially. And in order to, for example, escape from the surface of the Earth, you would need, so if this is you standing on the surface of the Earth and you wanted to actually escape Earth's gravitational effect, you would need to have some, assuming you don't have a rocket booster, it's all one initial burst of speed, and then you have to ride that all the way to the edge of the gravitational effect. You would need some kinetic energy. And that kinetic energy is the same amount as the negative gravitational potential that you start with. So the idea is when you're at effectively infinite distance, all of your kinetic energy has been converted into potential energy, you're at zero potential, all your kinetic energy is gone, and you've escaped Earth's gravity. This is how we calculated escape velocity, something you might have done back in Physics 1A, or in high school physics potentially. So, with that in mind, how does that apply to the electron system? Well, it's really a very similar process. Essentially, when a photon comes in, and the photon is drawn bigger than the electron here, that's not physically meaningful. So I can fit the photon symbol in, you can imagine you're sending in a photon that's going to strike this electron and give it however much energy that photon has. Now, the electron is going to have to use some of that energy to actually, so let's say the photon originally had some energy E. The electron is going to need to use some of that energy to actually overcome the potential well of the nucleus, so the electron will leave. So it will take some energy to actually escape from the potential well of the nucleus, and then whatever is left from that energy will remain as its kinetic energy. So this is the rest of the energy. So let's consider what we've actually done here. By decreasing the wavelength, we've given the photon more energy. So regardless of how much energy we have, the electron is always going to require some base amount of energy. We actually call this the work function, and there'll be a whole video discussing the mathematical representation of the photoelectric effect soon. It will take some energy to actually overcome the potential well of the nucleus, and then the rest of it is kinetic energy. So as we increase the photon energy, the kinetic energy of the resultant electron will get bigger and bigger because there'll be more energy left over when it's actually escaped from the metal. Now, so that means it makes perfect sense that the kinetic energy should increase. The reason the photocurrent doesn't change is because when we change the wavelength, we haven't actually changed the number of photons coming in. So now is the time to point out something important about this process. One photon can only interact with a maximum of one electron in this case. So the photon will come in, and if it strikes an electron, the photon will be absorbed and the electron will take its energy and leave. But the less photons we have, the less electrons that they can actually interact with. But if we keep the amount of photons the same, and remember that's linked to the intensity, so in this case we're keeping the intensity the same, you haven't been told that actually changed, only the wavelength changed, then we're not changing the number of photons coming in, which means we're not changing the number of electrons being struck by photons and ejected. And as a result, the total photocurrent, so the rate of electrons per unit time, the number per unit time of electrons being ejected, doesn't actually change. And all of this, the real point why we care about the photoelectric effect, is that this demonstrates the particle nature of light, because you can see that the electron ejection process is quantized. It's a particle-like photon interacting with the electron, and depending on how many photons there are, that actually influences how many electrons can be ejected. So if we have the same intensity, the same number of photons coming in, we have the same number of electrons going out.